Greetings. Let's say we have a set X, capital X, and it contains n elements. So I can say if, for example, it looks in this way, it's natural numbers from 1 until n. And that's also very often denoted as these square brackets with n inside, which basically is a different notation to denote a set that contains 1 through n elements. So it's an n element set. And it's of course bijective, means there's a same amount of elements in any other set of the same magnitude. Obviously, because this set, it represents, there can be a bijection to any other set of the same amount of elements. Just because here they're named 1, 2, 3 until n is a very systematical choice, and it's a good one for this illustration of this whole idea. But they could be A, B until the nth letter, or whatever names those elements have. But what will influence the idea here is only the amount of elements in a particular set. That's all. So counting them, and that's done with natural numbers anyway. So why not call them, like, why not call the elements or make the elements themselves the same as what they are counted by? So that's the set we're using, and what we want to also talk about is something called power set, which is the set of all subsets of this set of any magnitude that's possible. So it's the set of all potential subsets that this set can have. It's the whole set itself. It's the empty subset that contains nothing. It's the subset of each element isolatedly on its own. It's the subset of any two elements together from it. You know, so that these subsets are of course different from each other, but all the options that one can think of. And we want to see what is the magnitude of this power set. So for a particular set X, we have a power set of X, which is the set of all potential subsets. So I can give the example if it's not clear enough. Let's say our X is concretely given as 1, 2. Then the power set is going to contain the empty set, the whole set, and then in this case also the individual, the last option is also the individual elements that are there. That also always happens. So it's 1, 2, 3, 4. 4 elements. Magnitude of the power set of a set of 2 elements is 4. So if we have a 2 element set, it doesn't matter if it's 1, 2 or AB. If there's 2 elements in a set, the amount of different potential subsets, possible subsets that this set can have is 4. So that's stated as such. So that's how it looks. And now let's try to generalize it. So if we know that the magnitude of a set is n, then what is the magnitude of the power set of it? Well, let's look at it through binary numbers, and from that we will draw bijection and also look at some other ideas regarding this, and we'll get to the conclusion of this directly. So when we have, let's take for example, maybe that's easy now, the example of a 2-element subset, a 2-element set and all its subsets. So I will make a table and I will list in each row one of the subsets that's possible. What I mean is I will put a 0 below the number, below that one element of the, I will now say that my X is still at 1, 2, only this 2-element option. And if I'm talking about a subset where neither is contained, I will put a 0 in both. If one of them is contained, I will put a 1 below that one and 0 below the other. So there's also this inverse option to that. And if both are contained, I put a 1 below both. So 0 below that element if it's contained in this particular subset, and 1 if 0 if not contained, and 1 if it is contained. So we see I already did it. I made these 4 different options for binary number. For binary number on 2 digits. So we listed those out, and so we see 1, 2, 3, 4. So as before, count it again. This represents the empty set. This represents the set of 1 itself. This represents the set of 2 itself because we have the 1 below the 2, and this represents the whole set. When there's only 1s is the whole set, only 0 is the empty set, and 1 below one of them is just one of them. If we had 3 elements, it would get extended. And let's look at that option. So we can extend it to 1, 2, 3. And now let's look at the same table and extend it. And use binary numbers again to record those different subset options. So not only do we have these 4, but we have a third element, let's say this 3. And let's say that we extend it and we put 0 of the third element. But what we have to do is we have to double the amount of options to exactly double it. Because we also need the option where the third element is included. Indeed, we will need, again, 4 options, because we will copy what happened to 1 and 2 here, but for the new option of 3 being included, unlike in the first 4 rows. So I'll again do 0, 0 for the first 2, and 1, 0, and 0, 1, and 1, 1. So now we have an option of all 3 included, the last 2 included, first and third included, and when I say included, the remaining are always not included. First 2 not included, the last third, the third one included, and here you just see the pattern. So now we doubled it because of this. So it just took us 1 element to be added, and the amount of elements in the power set, in other words, the amount of subsets of that set, based on just the number of elements that original set contains, was doubled. So that basically tells us that the magnitude of a power set that has some new element added, let's say A is not initially contained in the set X, and then if I add 1 more element there, some element lowercase a, then that will basically be double the magnitude of this new power set will be the double of the magnitude of the original power set. Because I just added 1 element. And the option is, we have to just repeat all the initial options for the case that, first of all, it's the new element is not there, and the new element is there. So every added element multiplies the amount by 2. So this already tells us, or hints at something I will now reveal, and namely, if the number of elements in the set X is n, the number of subsets, all the different subsets it can have, is 2 to the n. So the power set's magnitude, therefore, is 2 to the n. And now let's look at it yet more systematically. We were talking in general about the set that has n elements, so we can call it, we can call the elements 1, 2 until n. And so, this question mark, let's just repeat it. So I can actually leave this here and we'll just delete this one because it's confusing to see it twice, it's the same thing. And now, let's reason it out with this table. We use zeros and ones to say, is that element there or is it not? And each row represented one subset, right? This subset was empty subset, this one was only containing 1, only containing 2, containing 1 and 2, containing 1, 2, 3 in this last case. So that was the idea. So now we have 8 potential possible subsets for a 3 element set. And for a 4 element, it's yet 2 times more. So that's the idea, it's 2 to the n, where n is the number of elements of the set, the number of subset of which we're counting. And these are all like binary numbers on 3 digits, listed out, in other words. Because we were using all these combinations, what we actually did when we look at the rows as numbers, we listed binary numbers of 3 digits. 0, if I read them as decimal numbers, it's 0, 110, 110, 1, 101, 11, 111. You see, if I read them as decimal numbers, they're actually not the same number. And they are all the potential binary numbers that we can write out if we are allowed to use exactly 3 digits. And that also hints at the fact that if we were counting the potential amount of binary numbers on 3 digits, where each digit can be either only 0 or 1, there are also going to be 2 to the n different options. So there's a bijection, equal amount of options, whether if we're talking about binary numbers on n digits or subsets of a set of n sets, n elements. And this can also be, if we're talking about it as counting, what we can say is we are counting the amount of words one can use with 2 letters the amount of 3-digit words. So if we're looking for how many 3-digit words there are on 2 letters, the counting idea for this and the counting rule is also 2 to the 3 in this case, or if I want to say, to generalize it, n letters, and how many digits are we looking for in the length of the word? We want 3-digit words. Well, it's going to be n to the k, n to the k, n to the k options. So this is a generalized idea. It goes directly from counting. We have 2 different letters in our allowed alphabet, namely 0 and 1, and we're looking at all the combinations, so 0, 0, 0, 0, 1, 0, and we do not care if the same letter is appearing twice in the word. That's not a problem. So when you are counting, it's the same. When you're counting a word of n letters and using basically, once again, a word of k digits long word, the amount of different possible k-digit words generated where these digits come from n letters is going to be n to the power of k. And because we only have 2 letters here, either that element is not there or it is there, represented by the zeros and ones, therefore the base of this exponential term is always 2. And then the n comes directly from the amount of elements of the original set. So the amount of elements in the power set is 2 to the n.